In Lecture 17, we introduced the idea of inheritance. The is a kind of relationship that you can create between, for example, a manager being a kind of employee. In this lecture, we're going to continue looking at matters to do with inheritance. First of all, on slide 2, notice that we've declared this class oops manager :employee to indicate that oops manager is derived from the employee class. Now, either we forgot to say public in front of employee, or we intentionally left out public in front of employee. And so what we get here is what's called private inheritance. And I say inheritance in quotes because it's not really an is a kind of relationship any longer. It's better to think of oops manager as being implemented in terms of employee, because what was public within the employee class is now going to be private through the oops manager class. And so it's not appropriate to say that an oops manager is a kind of employee, because behaviors that an employee has are not going to be visible through an oops manager object. Here on slide 3, we have an example program using the employee class and the oops manager class. And on slide 4, I have a diagram illustrating what the problems are here. Okay, so in slide 3, we're saying that Fred is an employee object. Fred is initialized with an ID of 6, a name of Fred, a rate of 63.33. Next, we declare an oops manager object called Glenn. And we'll assume that we have a properly written constructor for the oops manager class that takes the first 3 arguments, 7, Glenn, and 70.17, and passes those down to the base class constructor. Oops manager here also has a title, which is going to be boss, and a budget, which is going to be $750,000. So far, so good. Now the problem comes in here when we say Fred.getRate. This works fine because getRate is one of the public member functions of the employee class. But for Glenn, everything that was public in the employee base class is now private. And so when I try to find out what Glenn's rate is by saying Glenn.getRate, I'm going to get an access violation error from the compiler. If we take a look at our diagram here on slide 4, here's what's happening. I use this horizontal line in here in my class diagram to indicate the separation between the public facilities on the top and the private facilities underneath. So the public stuff is what can be accessed from within main or from within any other part of the code that's using employee objects. The private stuff cannot be directly accessed. The private stuff can only be accessed and modified by the member functions for the class. But over here for Glenn, the oops manager, notice where I have my horizontal line. The only things that are public within an oops manager are the 2 functions, setBudget and getBudget. Everything else, including public members for the employee class, print, setRate, getRate, those things are now private if I attempt to access those through Glenn. Continuing here in slide 3, I can set up P as a pointer object to an employee. P contains the address of Fred. Fred is an employee. And so if I say P arrow print, that will invoke the employee print function displaying information about Fred. But it turns out that because the inheritance I have for oops manager is private rather than public, I'm no longer permitted to take the address of an oops manager and store that into an employee pointer. So that is also going to be flagged as an error. Most of the time, private inheritance is probably created by mistake by simply forgetting to use the public keyword when you specify the base class for the derived class that you're creating. In addition to public and private, C++ offers a third sort of intermediate access protection specifier, protected. Now, when something is public in a class, that means that that facility, whatever that public facility is, whether it's a member function or a data member or a type, can be accessed from any code anywhere in the entire program. It's not restricted to just the member functions of the class. If something is private within a class, then only the code within that class itself, as well as any friend functions that you have specified, are going to be able to access those private things. Now, protected is sort of halfway between. Protected data can be accessed by the class code and friends, just like the private data can, but it can also be accessed from derived classes. That is, if I have a my class here with protected members, and from my class I derive a class called my bigger class, then the member functions in my bigger class will be able to mess around with the protected data contained within the base my class. Strustrup basically considers that he was sort of tricked into adding this protected access specifier. Relatively early in the design of the C++ language, one of the people at Bell Labs where he worked was using C++ to develop a windowing system. And this person kept showing up at Strustrup's office and saying, look, in my design for this windowing system, I really have to have protected data members, or I'm not going to be able to get my stuff to work. It's not going to be efficient. I really have to have protected data. So Strustrup relented, somewhat reluctantly, and introduced protected into C++. And later, Strustrup discovered that the same guy who had begged for protected data was now going around to Unix conferences and delivering talks about how bad protected data was and how he had had to eliminate all of the protected data from his windowing system code in order to get the bugs out. So, a bit of a slap in the face, to say the least. Now, protected member functions, which are functions within a class that only derived classes can call, are fine, because these member functions will control access to the underlying private data of the base class. Also, you can make an argument that protected data members are okay in what are called abstract classes. An abstract class defines an interface for a related collection of kinds of higher level classes, and we'll get into the details of how to define and use abstract classes next. But just to be absolutely clear, in this course, public data members that are not const and protected data members in a class that is not abstract are forbidden, are not to be used. I wish I could do an echo effect on that. No public data members other than const. No protected data members other than in abstract classes. So what do we mean by abstract classes? Let's take a look at that, starting here on slide 8. The classes that we've been dealing with so far, like employee, are real classes. You can really have an employee object in your program. The employee has an ID, a name, a rate, and various behaviors. We can get the rate, set the rate, get the name, print the employee, and so forth. Sometimes, though, some kind of category that it makes sense for us to talk about is abstract rather than real. For example, shape is a category of things that might occur in a graphical application. We talk about shapes without any confusion, and we know that kinds of shapes are lines, circles, squares, rectangles, polygons, and so forth. And we know that given a shape, we should be able to draw one, we should be able to rotate one, we should be able to scale it, we should be able to transform it to some new location. But we can only do those kinds of operations on specific kinds of shapes. That is, we can draw a line, we can draw a circle, we can draw a square, but we can't write down the code for drawing a shape. if I were a manager and I said to you, all right, write me a function that draws a shape on the screen, you would ask, well, what kind of shape are you talking about? You can't write a program to draw a shape if you don't know what kind of shape it is. So shape is an example of an abstract class. Likewise, option is an abstract class. What kind of option? Is it a European call option? Is it a European put option? Is it an American call option? So option is an abstract class or category that we have a general understanding about, but we can only describe and compute prices for specific kinds of options. Here on slide 9 is one way of implementing a shape class. We're saying that a shape has these three virtual functions: draw, rotate, scale. And we could come up with other operations that we ought to be able to do on shapes. But there's nothing really useful we can do to implement these functions. On slide 9, we've provided these silly implementations where the definition of each function basically says, sorry, you can't do this. So if you have a shape and you say you want to draw a shape, you'll get a message on the screen saying, no draw shape, and so on. Now, if we can't actually draw or rotate or scale shapes, then what good is it to have a class shape in the first place? Well, the benefit of this is that we might want to have collections of shapes. That is, we might want to have lists of shapes, or trees of shapes, or vectors of shapes, or whatever. In the case of options, we know that we can have a portfolio of options. We can't price an option without knowing what specific kind of option it is, but we can use this base class option to set up a portfolio, which perhaps is a list, of pointers to options, where actually each pointer to option is pointing to a specific kind of option, that is, a European call option with appropriate parameters, or an American put option with appropriate parameters. And then we can traverse through our portfolio, our list of options, to compute prices for each one of those. So here on my hand-drawn slide 10 is what a list of shapes might look like. We're using the struct SL node to keep track of each node in the list. The data is a pointer to a shape. Next is a pointer to the next SL node in the list. And the particular kinds of shapes in this list are a line, a circle, a polygon, and a square. And the data in each of these nodes is a pointer to a shape, which can point to specific kinds of shapes. To create a class that is truly abstract, what we do is to define our class to have at least one so-called pure virtual function. A pure virtual function is a function that has no implementation. And the notation that was developed to specify that a function is pure virtual simply involves using the equal sign and 0 instead of a body of code for the function. So in this example on slide 11, shape is truly an abstract class. A shape has a draw public member function. It has a rotate public member function. It has a scale function. But the shape class itself does not define any code for those functions. The functions are virtual, and therefore specific implementations of these functions, specific overrides of these functions, must be defined in each derived class. So if we say that a square is a kind of shape, then we have to implement draw and rotate and scale for squares. And if we say that a line is a kind of shape, we have to implement draw and rotate and scale for lines, and so on. If you specify at least one pure virtual function in a class, then it becomes impossible to declare objects of that class. In main, if I attempted to say shape space S and ran that through the compiler, the compiler would print an error message saying shape is abstract. You can't have this object called S. So here on slide 12, we have an example of an actual or concrete class derived from this abstract shape base class. This is class circle. A circle is a kind of shape. Is a kind of is indicated by public shape. And this class has a constructor which will create a circle by setting its horizontal and vertical offset for the center and also the radius. It has a destructor, which in this case there's no dynamic memory we have to deallocate or anything. So we're simply displaying a message to indicate when the destructor is called. Then we have to write the code for drawing a circle, which is a little more complicated than I'm going to try to do here. We have to write the code for rotating a circle. Now, rotating a circle is completely trivial. We can implement this function by creating an empty body because a rotated circle is indistinguishable from the original circle. Down in the private section, we need to have the data necessary to keep track of the state of the circle. Each circle object is going to have an XY center position as well as a radius. We're not going to allow default circles, and so we've declared the default circle constructor to be private. Similarly, here we have a concrete class, polygon. A polygon is a kind of shape. Polygon has a constructor and a destructor, draw, rotate, so on and so forth. Now, the data members that we need to keep track of a polygon are quite different from the data members that we had for a circle. In the case of a polygon, we're going to need x and y coordinates of all of the points, and here we've chosen to do that by using dynamically allocated arrays of ints for the x coordinates and for the y coordinates. We also have to keep track of the number of elements, the dimension of these xy coordinate arrays. And as a circle, we're not going to allow default polygons. If you want a polygon, you have to specify the x coordinates, the y coordinates, and the dimensions of those two arrays. Okay, those are the three parameters that you're required to give to the polygon constructor. The implementations of these polygon functions are shown here on slide 14. We're not showing draw and rotate, but here are the constructor and the destructor. In the constructor, we're first examining the value of the dimension d to make sure that that's a positive number. We can't have a polygon of 0 or fewer points. So, for the array of x coordinates, if d is greater than 0, we're going to allocate a new int array of size d. Otherwise, we'll set xa to 0, that is the null pointer. Likewise, for the y coordinates, if d is greater than 0, we'll set ya to point to a new int array of dimension d, otherwise null pointer. And finally, we'll set dim, the dimension, to either d if d is greater than 0, or 0 if d is less than or equal to 0. Now, once we've established these dynamically allocated arrays of ints for the x coordinates and the y coordinates, and we've also established the dimension, in the body of code, we'll use a for loop to step our loop counter I from 0 up to 1 less than dim, and we'll copy the values from the input arrays, px and py, into the current polygon object's internal arrays, xa and ya. Now, because we use dynamic allocation in the constructor, we'd better remember to delete those dynamically allocated arrays in the destructor. In fact, this is why we use dynamic allocation in the first place. It would frankly have been simpler for us to use a couple of vectors of ints, since we know about the vector class now. But I wanted to remind everyone that you have to undo in the destructor any resources that you allocated in the constructor. In this case, we have to delete these dynamically allocated int arrays. As we did in the circle class, we're also displaying a message here that will appear on the screen each time this polygon destructor is called. Here on slide 15, we have an application using these kinds of shapes, circles, polygons, and in this application we also have a square, which we didn't show the implementation details for, but it would be similar to circle and polygon. Now in this application, because the shape class is abstract, as we talked about before, if we attempted to say shape and then an object name like S1, the compiler would yell at us that shape is an abstract class and it's not possible to create an object whose data type is an abstract class. But we are allowed to create circle objects. C1 here is a circle object. S1 here, which maybe I should have called this SQ1 to differentiate it from the shape, but anyway, S1 is a square object, and P1 is a polygon object. Now, the array X and the array Y here contain the XY coordinates of the 5 points that make this polygon P1. So the polygon P1 has 5 points in it, which are 1, 1, and then 3, 1. Notice that the X coordinate is 3 and the corresponding Y coordinate is 1. And then 8, 2, 9, 3, and 4, 8. So this polygon would have 5 vertices and 5 sides to it. Now that we've created those specific kinds of shapes, a circle, a square, and a polygon, let's draw each one. C1.draw we'll call the circle draw function. S1.draw is the square draw. P1.draw is the polygon draw function. When I hit the closing curly brace at the end of main, the application is over. These local variables C1, S1, and P1 are deallocated, and in the process the destructors for those things are called. Alright, so the output on slide 16 of the program on slide 15 would show first the circle being drawn, the square being drawn, and the polygon being drawn in some sort of graphical screen. And then I want you to notice that the destructors are called in the opposite order in which the objects were created and their constructors were called. So the circle C1 was created first, followed by the square S1, and then the polygon P1. And when we leave the main function and the destructors get called, it's the polygon that's destroyed first, then the square, then the circle. Okay, so this is not an accident. This is not a feature of the GNU C++ compiler. This is specified in the language that destructors are called in the opposite order of constructors. So this simple program on slide 15 created and drew 3 shape objects, namely a circle, which is a kind of shape, a square, which is a kind of shape, and a polygon, which is a kind of shape. Of course, a real graphical application would have to manage some arbitrary number of graphical objects, that is, arbitrary number of shapes that are created and destroyed by the user on the fly. So on slide 17 and on slide 18, we're showing a slightly more sophisticated, still very simple, but slightly more sophisticated program that uses a vector of pointers to shape to keep track of the shapes that currently exist in the application. So we've included vector, and in main we have declared SV as a vector of pointer to shape. We have not formally introduced the vector type yet in FC2. That will come in a later lecture. But for our purposes, you can think of a vector as being like a Python list. That is, you can subscript its items starting from 0, And whereas for a list, you can use append to add an item to the end of the list, for a C++ vector, you use a function called pushback instead. Initially, that vector is empty. Now, to add shapes into the vector, we're going to use new to create a kind of shape in the dynamic memory area, that is in the heap. Here we're creating a new circle with a center located at 5, 5 and a radius of 1.5. We'll get back from that a pointer to circle, and we're going to use pushback to push that pointer to circle onto the end of SV. That is, because a circle is a kind of shape, we can store this pointer to circle in our vector of pointers to shapes. Then in the next line, we're doing the same thing with a square. Here we're allocating a new square with its lower left corner at 0, 0 and its upper right corner at 10, 10. We get back from new a pointer to a square, and we push that to the back of our vector of pointers to shapes. Notice in both of these cases, new circle and new square, that we're using the constructor to create an unnamed circle and an unnamed square. In the same way that if we were to say new int, that would create a new unnamed int in the heap. Creating a polygon is a little more complicated because, of course, we have to have our array of x coordinates and corresponding array of y coordinates of the same size. And then we can allocate a new polygon where the points are at those xy coordinates, and dim is the number of points in the polygon. So now we have SV is a vector of 3 pointers to shapes. The first pointer is actually a pointer to a circle, the second pointer is actually a pointer to a square, and the third pointer is actually a pointer to a polygon, but since these are all kinds of shapes, we can treat them as pointers to shapes. Then we're using our for loop here, with I going from 0 up to 1 less than the size of our vector. We're going to first draw the currently pointed to shape. So SV sub 0 is going to be pointing to a circle, and we're going to call the circle draw function. Then we're going to scale the pointed to object to double its size and redraw the object by calling the draw function again. So SV sub 0 is actually pointing to a circle, so we're going to draw the circle, we're going to double its radius, and we're going to draw it again. SV sub 1 is pointing to a square, so we're going to draw the square, double the size of the square, and draw it again. And then SV sub 2 is pointing to a polygon, so we'll draw the polygon, double its size, and draw it again. Now normally, once we have used our various shapes, since we have dynamically allocated them, we would need to delete them, and we would probably have a separate loop that would do that. But here we're crowded for space on these two slides, 17 and 18. So I have put the deletion of the allocated objects right inside the loop. And actually here I see I made an error. Instead of saying delete star IT, there is no such thing as IT in this program. We're not using an iterator, we're using an integer subscript. So that line should say delete SV sub I. I have actually made that correction in these lecture 19 notes for this course. And that's it. So we've got this little program on slides 17 and 18 that sets up a vector of pointers to shapes, then allocates 3 kinds of shapes on the fly, on the heap, storing those pointers into our vector. Then we traverse through the vector and draw and scale and draw each shape, and then delete the shape when we're done using it.